Let's look at a real-life example of a vector field that derives from a potential. And this is the gravitational field. So the gravitational field can be defined in terms of the gravitational potential. And the relation is that the gravitational field G, which is a vector, is defined as the minus gradient of the potential phi. Okay? So the question here, this problem is obtain the gravitational field for a point mass whose gravitational potential is in spherical coordinates given by this. Okay? Before starting the calculation, you already know what the answer should look like, right? So if you have a mass m, what does this potential field look like? So this is a potential field which has some constant times m, so this will be all constant for a given mass, and then it's divided by the distance to the origin, or the distance to the mass. So this means that the scalar field is decreasing as we move away, at least decreasing in absolute value. Although since we have a negative sign here, this means that the scalar will be very negative near the mass, and it will become less and less negative as we go further away from the mass. Okay? So what if we draw the surfaces where the potential is equal? These are called equipotential surfaces. How will this look like? These will look like spheres. So in this sphere, the potential has a certain value. In the next sphere, the potential will be slightly smaller. Okay, so this is another sphere like this, and so on. We can define spheres of equipotential. So in these spheres, the potential is the same. So this will be potential equals constant. Now, we know that the gravitational field will be the minus gradient of the potential. But you already know when we studied the gradient that the gradient is a vector which points in the direction of increasing potential. And if we add a minus sign, this means that this minus gradient will point in the direction of decreasing potential. And also that this vector, the gradient, is a vector which is always perpendicular to the surfaces of constant potential, right? We saw that as a property of the gradient. Therefore, this means that the electric field, the gravitational field, will be a vector always pointing towards the mass and always orthogonal to the surface of equipotential surface. So you will get this gravitational field always pointing toward the mass, but always orthogonal to the equipotential surface. Okay? And this makes perfect sense. You know that this will be the gravitational field for a mass. The force experienced by a test mass will always point towards the mass. We also know that this force should be inversely proportional to the square of the distance. So we know that this is the gravitational field around the mass, yeah? And it's always pointing in the minus radial direction, er hat. So we know this result, but now let's derive it from the potential. So in order to do this, we write G, the gravitational field, is the minus gradient of the potential, which is equal to the minus gradient of this, minus Gm divided by R, which is the value for the potential. Okay? So in order to calculate this, we can take the minus with the minus cancels out, so we end up with a plus. We can take the constants outside. So we must find the gradient of 1 over R. Okay? Which means that we must find a vector, which is the partial derivative with respect to x of 1 over R, the partial derivative with respect to y of 1 over R, and the partial derivative with respect to z of 1 over R. So now we are a bit of a problem, right? How do we do the partial derivative with respect to x of 1 over R? R is the distance to the origin, so what's the partial with respect to x? Might seem a bit difficult until you realize that R is simply, by Pythagoras' theorem, it's simply the square root of x squared plus y squared plus z squared. It's just the distance from the origin to an arbitrary point x, y, z. So knowing that this is the expression for R, we can now calculate the partial derivative of 1 over R with respect to x. So the partial derivative with respect to x of 1 over r can be written as the partial derivative with respect to x of what? Of x squared plus y squared plus z squared to the power minus a half. Do we agree? That will be 1 over r, because r is the square root. So now how to do the partial of a function to some power? You already know how to do that, right? First you bring down the power to multiply, so minus 1/2 times the derivative of the parenthesis, which is with respect to x, so that will be 2x. And now times the original function in the parentheses, x squared plus y squared plus z squared, but to a power that is 1 less than the original one. So minus 1/2 minus 1, so minus 3/2. Okay? So these 2 will cancel out with these 2, so we will end up with minus x divided by this to the power 3/2. Right? But this to the power 3/2 is nothing else and nothing more than the radial distance to the power 3, right? Because the radial distance is the square root of this. So therefore, if you raise that to the power 3, you end up with this. So this means that this is equal to x to minus x divided by r cubed. Okay? Now, similarly, you can use identical logic to find the partial of 1 over r with respect to y. And this will be equal to minus y over r cubed. And the partial with respect to z of 1 over r will be equal to minus z over r cubed. Okay, so you can find the partial derivatives in that way. And therefore we can now build, so let me add this in a block. So now we are ready to substitute these results into the gravitational field. So we substitute those here and we get that G is equal to Gm times minus x over r cubed minus y over r cubed minus z over r cubed, which we can write as minus Gm over r cubed of x, y, z. And now if you realize that x, y, z, this vector is equal to r vector, so you can write this as minus Gm over r cubed times r. And now you can further realize that the r vector divided by the r scalar is equal to er hat. It's the normal vector in the direction of r. So therefore you can take one of the r's here to divide with r, and you get minus Gm over r squared times er hat. Okay? So in this way, we have shown that the gravitational field can be calculated as the gradient of the scalar of the gravitational potential. Good. I hope that was clear, and I will see you in the next video. Thank you very much.